When field lights failed during wartime, darkness became more than an inconvenience. It meant lost signals, unread maps, stalled repairs, and broken coordination. Batteries were heavy, fragile, and rationed. Supply lines failed regularly. In response, soldiers and engineers fell back on a principle older than modern electricity itself: chemical power drawn from common materials. The rust and vinegar trick was not folklore. It was a field-expedient application of electrochemistry that could restore communication, power low-draw lamps, and keep instruments alive when standard equipment went dead. This section explains the historical roots of the rust and vinegar method. The concept traces back to early galvanic experiments in the 18th century, but wartime necessity forced its practical use. Soldiers did not need refined copper plates or laboratory acids. Iron scrap, rusted nails, vinegar from rations, and bits of wire were enough. Manuals for field telegraphy and emergency signalling referenced improvised cells as a last resort power source. While never intended to replace issued batteries, these cells provided critical low-voltage output in moments when no other option existed. This section clarifies what rust actually contributed to the system. Rust itself was not the power source. It was, really just evidence of iron's readiness to react. The true engine of the system was the chemical difference between two metals in an acidic solution. Iron served as the sacrificial electrode. A second metal, often copper, scavenged from wiring or cartridge jackets, acted as the stable electrode. Vinegar provided the acid needed to allow ions to move. Rust increased surface area on iron, speeding the reaction and, making weak materials more effective. This section explains how the improvised field cell actually generated electricity. When iron and copper were placed into vinegar without touching each other, a small electrical potential formed between them. Iron slowly dissolved into the solution, releasing electrons. Those electrons travelled through an external wire toward the copper. This flow created usable current. One cell produced little power, but several cells linked together increased voltage enough to serve practical purposes. Soldiers understood this intuitively through results, even if they lacked formal theory. This section describes how soldiers assembled the system under pressure. A container was filled with vinegar diluted slightly with water to conserve supplies. An iron object, such as a nail, bayonet fragment, or rusted tool, was submerged on one side. A copper strip or wire was placed opposite it. Each metal was connected to a wire leading out of the container. Multiple containers were then linked metal to metal in sequence. This created a chain of cells capable of powering small bulbs, signal lamps, or field telephones for short periods. This section shows what the system was realistically used for in wartime. The rust and vinegar cell was not used to flood a tent with light. It was used for precision tasks. Soldiers powered faint indicator bulbs to check circuits, revive telephone lines long enough to pass messages, and ran small lamps inside equipment cases where, honestly, even dim light was enough. In winter campaigns, these cells sometimes powered improvised heating wires to keep instruments from freezing solid. This section explains the limitations soldiers learned to respect. The output was weak and inconsistent. Vinegar strength varied. Iron quality mattered. The cells degraded quickly as iron dissolved. field manuals warned that the system was temporary by design. Its value lay in minutes or hours of function, not days. Soldiers learned to treat it as a bridge between failure and resupply, not a replacement for issued gear. This section provides a modern application grounded in the same principles. Today, the same method can be used to understand emergency power generation without relying on modern batteries. A single cell can light a low-draw LED long enough to demonstrate function. Several cells linked together can power a small radio circuit or emergency signal light. The steps remain the same: separate metals, acidic liquid, external connection, and, well, patience. The value lies not in brightness, but in reliability when nothing else works. This section explains why the method remains relevant despite modern technology. Modern power systems depend on manufacturing, logistics, and stability. The rust and vinegar method depends only on chemistry and, honestly, a bit of ingenuity. That independence made it invaluable during war, and, it really keeps it relevant for survivalists, educators, and historians today. It represents a mindset that treats failure as a problem to be solved, not an end point. This section ties the lesson back to wartime resilience. The true lesson of the rust and vinegar power trick is not electricity. It is adaptability. Soldiers who understood the basics of materials and reactions could restore capability under extreme conditions. That knowledge travelled quietly through camps and units, passed hand to hand, and preserved function when official systems collapsed. If this deep dive into forgotten field ingenuity added real value to your understanding of wartime survival and historical problem-solving, subscribe to the channel, share this guide with fellow history enthusiasts, and help preserve these lessons that still matter today.